and it will be uploaded soon. Okay. Any other query?
Yeah, ma'am, this is out of this tails one. The quiz 2 marking, the email has come saying that your answer sheet or whatever has been uploaded. But when I went into the website, the old quiz 1 only is there. Quiz 2 is not yet uploaded, but the deadline for responding is, I think, today or tomorrow, I think, 26th.
Sir, it's tomorrow. I have informed ma'am.
Okay.
What is that?
The same thing I told this ma'am like 2 minutes before.
Okay, you also have the same problem. Okay.
Yeah, sir. The PDF is of qualified exam, and we have to recheck for quiz 2.
Yeah.
Yeah, she informed.
Okay.
Yeah, just wait for 1 minute. I'll be back.
Sure.
Hello, am I audible? Yes, so let's start.
Yes, ma'am, you are audible.
So in today's sessions, we'll first learn what is a DFS method and what are the properties we have for DFS method. So that means what are the things we can do using DFS method for any graph. Okay, and then we'll go through the topological sorting. And after that, I'll take all your doubts from activity and practice assignment. So that's the plan for today's session. So let's start with the DFS process. So first of all, what is our aim here is, or what we want to do. So we want to answer the reachability question. Okay. So reachability question means, is it possible to reach from a vertex U to another vertex V via a path in a graph? Okay. So if we have a graph, then we know that in a graph we have two types of things. One is vertices, another one is edges. So our reachability questions deal with that. Is it possible to reach from a vertex to another vertex via path? My voice is clear, right? Is there any lag or issue?
No,
No,
ma'am,
ma'am.
it's clear.
Yeah. So for answering this reachability questions, we actually have two methods. One is our BFS, another one is our DFS. So what is the difference between these two methods is this BFS method works in a very strategic way. So that means here you have a particular procedure. So first we observe our source vertex, and then we go to the neighbors of source vertex and then their neighbors. So for example, here we have a source vertex. We'll go to the neighbor of this source vertex. And then one by one, we explore these neighbors too. Okay, so that means this this BFS process work in a very strategical way. So we'll start with one vertices, go to their neighbors, and then neighbors. But what happened in DFS process? So in DFS process, we randomize this thing. Randomize this thing means, suppose you have a vertex U, and for this vertex, you have several neighbors. So suppose I have some V1, V2, V3, and V4. So that means I have a vertex U, and for this vertex, I have 4 neighbors. So in DFS process, what we do, we'll choose one of the neighbors and proceed in the new direction. So for example, so there are these 4 vertices. So you can choose any of the neighbors. So suppose I choose V3. So then what I'll do, I'll explore this vertex and then I'll go to V3 and then explore the neighbors of V3 if there are any other neighbors of V3 possible. So that means if there are neighbors of V3, I'll go to their neighbors. So we can choose any one of the neighbors, right? So here we randomly choosing the neighbor and exploring it further until and unless we reach at a dead end. Dead end means you come across a neighbor whose, there are no new vertices to explore. Okay, so I'll explain this with the graph too. So let's go to the DFS search, right? So DFS search means same as BFS search. So let me take this one. Okay. So as you observe in BFS process, for BFS process, instead of stack, we have a queue, right? So what does queue means? Queue means first in, first out. So that means whatever element is there at the first position in your queue, that element will got explored at first place. But in DFS process, in place of queue, we have a stack. Okay, so stack means you can observe that a stack of books. For example, in your table, you have some stack of books, right? So in that stack of book, what happened? That book which were placed at the top, that book will be chosen at first. So that means the stack work over the last come first in principle, right? So over a stack, a stack of books, we know that if you want to choose a book, that book will be the last book placed over that particular stack, right? So the stack means it's again. So what is queue and stack is? So queue and stack is nothing but a way to arrange some elements. For example, you have suppose you have 10 books, right? So what you can do, you can place those books over the queue, or you can place those books as a stack, right? So for example, you place those books over a queue. So this is your queue, and suppose this is the first position of your queue. So this is the queue method. So queue method means just a method to arrange some type of elements. And stack is also a method to arrange some type of elements. So, but the basic difference between queue and stack is, so queue says first in, first out. So that means whatever comes first, that element got explored at the first place. But in the stack, whatever comes the last, that element got explored at the first place. Okay, so this is a basic difference between queue and stack. So in BFS process, we used queue for arranging the explored vertices. And in DFS process, in place of exploration, we will arrange the suspended vertices. Okay, so now what is this suspended vertices are? I'll explain in a minute. So here we are arranging the suspended vertices. So for example, we have this same airline graph. So in this graph, suppose I want to apply a DFS search. Okay, so for applying a DFS search, as like in BFS, we will choose a source vertex. Okay, so here we will choose a source vertex and then we'll start our DFS search. So suppose we choose a source vertex named to be vertex number 4. Okay, so then what does DFS says? DFS says that mark this vertex 4 and now suspend this exploration of vertices 4 and choose any one of the neighbors of this particular vertex 4. Okay, so that means we are doing things in a random pattern. So in the next step, what we will do, so we mark our source vertices, and then we will suspend this source vertex. Okay, so whenever suspension means we just forget about that vertex now for a time being. Okay, so we just forget about this particular vertex for time being, and we write down the suspended vertices in our stack. Okay, so this is our stack of suspended vertices. We'll write down the suspended vertex in our stack at the first place. Okay, so this is the first place. But again, stack works in last come first in principle. So I'll also explore what we will do all these suspended vertices. Okay, so the first step of BFS is so the first step of DFS is, first of all, mark the source vertex, then suspend that vertex and choose any of the neighbor of source vertex. Okay, so here we have three choices. You can choose any of the neighbor of vertex number 4. So the neighbors are 0, another neighbor is 3, and the next neighbor is 7. So that means you can choose among 0, 3 and 7 any neighbor, whatever you like. But in our graph theory, we made a convention that we always choose the least number first. So that's why we are choosing the number 0. Okay, so it's our convention. It's up to you. You can choose vertex number 3. You can also choose vertex number 7. But for generality, we will choose whatever the number is least, right? So among 0, 3, 7, 0 is the least number. That's why we choose 0. So now what we will do, we'll suspend 4 and explore 0. So now what we'll do, we'll look the neighbors of 0. So is there any new neighbor where we can go? So that's a question. So that means we need to find out new neighbors at every step. So for example, here as we reach to 0, our question is there any other new neighbors which haven't been suspended or which haven't been explored yet? From 0, can we reach to some of the new neighbors? So the answer is yes. We have 2 new neighbors, which is 2 and 1. And also we just change the visited status as we did in BFS process. So whatever thing or whatever vertices got visited, we just change this visited status from false to true. Since vertex number 4 got visited, so we change it to true. And similarly, vertex number 0 got visited. That's why we change it into true. Okay. So now from 0, it is possible to go to a new vertices, right? And the possibilities are the vertex number 2 or vertex number 1. So again, what we will do, we'll suspend the exploration of 0 and go to any of the new vertex. So here you can choose between 1 and 2, but again, we choose the least one. So that's why we will choose 1 and move ahead. So here we are suspending 0. So whenever we suspend 0, we'll add that 0 in our stack. Okay, so now in the next step, we do the same thing for vertex number 1. So again, we'll check the possibility to get something new from vertex number 1. So the answer is yes, because the vertex number 2 is not visited yet. So we can go to vertex number 2 using vertex number 1. So what we will do, we'll suspend the exploration of vertex number 1 and go to vertex number 2. Okay, again, suspension means just forget about that vertex for time being. Okay, so we'll use the suspension in our next step. But for time being, what is a suspension means? Suspension means forget about that thing for time being and go to the new place. Okay, so here we will suspend the exploration of vertex number 1 and go to the new unvisited vertex, which is vertex number 2. Okay, so we'll suspend 1 and explore 2. But here from 2, we got stuck, right? So here there is nothing new we can get from vertex number 2. The only neighbors of 2, the neighbors 2 have is 0 and 1, right? But both vertices are already visited. So it's not a new information for us, right? So what we will do, okay, so here we reach at a dead end, right? So at vertex number 2, it is a dead end. We cannot get anything new from vertex number 2. So whenever such situation occur in DFS process, what we will do, we'll backtrack our process. So backtrack means you will backtrack which vertex, you will backtrack to that vertex which lead us to vertex number 2. And then I can do the backtracking until and unless we reach a point where we can get a new vertices. Okay, so what does that mean? So it means that, so since from vertex number 2, there is no new information we can get. So we will backtrack from vertex number 2 to vertex number 1. And as you can observe, as we backtrack from vertex number 2, we'll go to vertex number 1. And now we will remove this vertex number 1 from the stack of suspended vertices. So that means we enter a vertex in a stack of suspended vertices when we suspend it, and we will remove a vertex from stack of suspended vertices when we backtrack it. Okay, so that means add when suspended and remove when backtracked. Okay, so this is the formula, or this is the thing we will use to add and remove any vertex from our given stack of vertices. Okay, so now as we, so when we reach to the vertex number 2, we observe that there is no new vertex which is connected to vertex number 2. So that means we cannot get any new information from vertex number 2. So we will go back to that vertex which lead us to vertex number 2. And that vertex is nothing but vertex number 1. So we'll backtrack to vertex number 1, and then we observe the same thing for vertex number 1. So that means, is there anything new vertices we can visit from vertex number 1 or not? So the answer is no, right? So from vertex number 1 also, there is no new vertex which we can visit, right? So what we'll do, we'll again backtrack to that vertex which lead us to vertex number 1. And that vertex is which vertex which lead us to vertex number 1? Anyone?
Ma'am, 4, ma'am. 4.
0,
Ma'am.
0, 0.
0.
Right? Because when we suspend
So,
0, we explode 1.
0. So,
Right.
0. Yes.
What we'll do, we'll backtrack to vertex number 0. And as we backtrack to that vertex will be removed from our stack. So the next step will be, we'll backtrack to 0 and remove that 0 from our stack of suspended vertices. Now same thing we observe for 0. So you can observe here that from 0 also, there is no other new unvisited vertices are connected. So what we'll do, we'll again do the backtracking. So now we will backtrack to 4. So as we backtrack to 4, we'll remove this 4 from our stack of suspended vertices. Okay. Now again, the same thing we observe for vertex number 4. So the question is there any new vertex which is connected to vertex number 4 or not? Okay. So here the answer is yes. So there are 2 unvisited vertices which are connected to vertex number 4. So again, we can choose any one of them, but as our convention says, choose the least one. So what we will do, we'll suspend the vertex number 4 and go to vertex number 3. Okay. So in the next step, we'll suspend vertex number 4 and explore the vertex number 3. And again from 3, we ask the same question, is it possible to get something new information from vertex number 3 or not? Okay, so the answer is yes, because there are 2 unvisited vertices, which is 5 and 6. So we can go to any one of the vertex, but again, we choose the least one and go to vertex number 5. But as we go to vertex number 5, we will suspend vertex number 3. So that means we will forget about vertex number 3 for time being and go to vertex number 5. Okay. So we suspend the vertex number 3, go to vertex number 5. And again from 5, we'll ask the same question. Is it possible to get something new information from vertex number 5 or not? So answer is yes, right? Because there are 2 unvisited vertices present, the vertex number 7 and vertex number 8. So you can choose any one of them, but as our convention, we'll choose the least one. So that means we'll suspend the exploration of vertex number 5, go to vertex number 7. And at, okay, sorry, I think
But
I
6
forgot
is
about
not covered, ma'am. 6
Yeah,
is not covered.
6 is also there. So that means we can choose any of these 3 vertices. So we'll choose the least one. So go to vertex number 6. Now here at 6, you can observe that we reach at the dead end. Right? Because from 6, we cannot get any new information. Is that right? Any doubt in this one? Why we stuck at vertex number 6?
Because 3 is already covered.
Yeah.
So 6 has no neighbors. So
Yeah, no
that's the
new
reason.
neighbor, right?
No new neighbor.
It's nothing new we can get from vertex number 6. So what will be the next step at this stage? Can you guys tell?
We will back.
Go back to 3, go back to 4, go back
to
to
5.
5.
Right?
5. Yeah,
Yeah,
5.
so what we'll do, we'll backtrack to 5. So as we backtrack to 5, we'll remove that from our stack. And again, from 5, we have 2 new choices, which is vertex number 7, vertex number 8. So you can choose any one of them. So we can choose vertex number 7. So go to vertex number 7, explore it, and again go to vertex number 8, vertex number 9. And at 9, we again reach at a dead point, right? So this is also a dead end to us. But what happened at vertex number 9? So from vertex number 9, we'll start backtracking. So we'll start backtracking from vertex number 9. So we'll backtrack to 8, we'll backtrack to 7, then we'll backtrack to 5, and then from 5, we'll backtrack to 3. So from 3 you will backtrack to 4. And why we are doing this backtracking? Because it's just a formality now. Because we know that every vertex has got visited, but we are doing this backtracking so that we can empty our stack. Okay, so the reason for backtracking at the end is so that we can empty our stack, because you know that in a stack we can enter a vertex when it got suspended, right? Any in a stack we will remove that vertex when it got backtracked, right? So here we want to empty our stack, empty the stack of suspended vertices. So that's why we will backtrack to the source vertex. So here what is our source vertex? Source vertex was vertex number 5. So from 9 we will backtrack to vertex number 8. From 8 we'll backtrack to vertex number 7, then go to vertex number 5, then go to vertex number 3, and then wapas we'll complete our circle to vertex number 4. Okay, so we are doing this backtracking at the end because it's just a formality. Now we know that every vertex got visited, so we cannot get anything new. But we are doing this so that we can empty our stack. And the thing is that DFS process will stop when the stack is empty, right? So when the stack of suspended vertices got empty, there your first DFS scan will got stopped. Okay, so this is the case. Now, here the idea is simple. So the idea for BFS and DFS is very intuitive, right? So in BFS process, we use the strategy that first select the source vertex, go to their neighbors, then from neighbors, go to their neighbors, and so on, right? And DFS also, the strategy is simple. Select the source vertex, go to its one of its neighbor, then go to its one of its neighbor, then go to one of its neighbor. And if there is nothing new, just come back to this one, come back to another one where we can find something new information. Okay, so this is the general idea of both processes. But why we want this visited and the stack of vertices on all this terminology is so that we can make this particular method for larger graphs too. So that means if you want to command these two methods over your computer, you need some sequence, right? That how this particular method will work. So for creating that particular sequence and all those things, we need all these terminology. That what are the steps that this particular process will apply over a graph, right? So in this case, it's easy since we have only 9 vertices. But assume that you have a graph with thousands of vertices, right? So in that case, it's not possible to manually apply this DFS process or BFS process. So that's why we have created some terminology or some things so that we can systematically apply this particular scan over any graph, no matter how large or how small that graph is. Okay, is that clear?
Yeah.
Yes, ma'am.
Yeah. So this is BFS and DFS process. So is there any doubt in BFS or DFS process?
So in the BFS, you cover the complete level before you go to the next levels, right?
Yeah, correct. Before go to the next level, you have to complete, you have to explore each and every neighbor, whatever you have selected.
Whereas in DFS, you go to the depth and then come back again. Then
Yeah,
again go to the next depth. Okay.
yeah, correct. So we'll proceed in one direction until and unless we reach at a dead end, and then come back from that, and
Yeah.
at whatever step you will get something new to explore.
Sure.
Okay. So this is all about BFS and DFS process. So basic differences we know, right?
But it
Now,
has any advantage? I mean, there's a scenario where one has to use, one should not be used like that.
yeah, so these two methods have their own properties. So
Okay.
they both are important. So for example, BFS process, here you can observe that whatever path we discovered in BFS process, that will be the shortest path. But in DFS process, it need not to be a shortest path. For example, here in the above graph, we found a path between the vertex number 4 to vertex number 7. Like we go to 4, we go to 4 from, we started with 4, go to 3, and then go to 5, and then go to 7, right?
Right.
So this is a path obtained in DFS process.
Correct.
But if you apply BFS process will directly use this particular edge from moving 4 to 7. So whatever path we will get in BFS process, that will be the shortest path.
Okay.
Okay. So for finding shortest path, we use BFS. And why we use DFS? So the reason is one is for finding cycles. So
Ma'am, there
how
seems to
we
be a mistake in the slide text. Paths discovered by BFS are not shortest path, unlike BFS. I
yeah
think
yeah
one of it should be DFS, right?
yeah.
Yeah. Okay.
So path discovered by BFS are shortest path, unlike as DFS. So we can change this. Unlike DFS. Yeah, there is mistake. Sorry, I didn't read it. But yeah, so we use BFS for finding shortest path. We use DFS to judging whenever it is possible to get a cycle in a graph or not. Okay, so for this cycle thing, so we use the DFS for this. For the cycle thing, we actually work over the two steps. So for example, we first of all, so in this lecture only, we will cover what is a DFS numbering. And then using this numbering, we'll go to some edges. So that is forward edges, backward edges, and cross edges. And using these edges, we can judge for a cycle. Okay, so this is the path for observing that in a given graph, is it possible to find a cycle or not? Right, you guys familiar with cycle, right? For example, this sequence, start with 0, go to 1, go to 2, come back to 0. This is a cycle in a graph. So if we have a graph and over that graph, if you compute DFS numbering, then using that numbering, if you judge the forward edge, cross edge or mid edge, we can get an idea that is it possible to get a cycle in that particular graph or not. Okay, so these are the major applications of DFS and BFS process. But before that, I would like to introduce what we understand by a tree in a graph, or in general what is a tree to us. Okay, so the useful feature can be found according to DFS vertices. Yeah, DFS numbering, as I mentioned, we use DFS numbering to find the cycles. But before that, let me introduce what is a tree. Okay, so tree is nothing but a type of graph. So a tree is acyclic connected graph. Okay, so that means a graph which is acyclic means there is no cycle. And connected means we can reach from any vertex to any other vertex using a path. So we can reach from any vertex to any other vertex. Okay, so a tree is nothing but a acyclic connected graph. Acyclic means there are no cycles, and connected means it is possible to reach from a vertex to another vertex. So I'll just take one example. So suppose I'll give you this particular graph, and I'll ask you, is it a tree? Is this graph a tree? What
No.
will be your answer?
Yes, it's a tree because it goes, can every vertex can be reached.
Yeah, we
And
can
then
reach any other vertex.
and there is no cycle. There is no cycle.
Yeah, there is no cycle, so that's why it's a tree. Now, is it a tree, this particular triangle?
No, ma'am.
No, because we have a cycle here, right? So it's very easy to judge a graph is a tree or not. Just by looking at the graph, we can say. For example, I'll give you this graph. So suppose these two segments unionly take it as a graph. So now, is it a tree?
No. Yes, it is a tree because it's a cyclic and
Yeah, but
but
they are disconnected, right? These two components are
yes.
disconnected.
Mhm.
You cannot reach from this vertex to this vertex, right?
Okay.
So
Whole as a whole in a square, yes, there is no, but two different trees.
yeah, two different trees. So this is not a tree, but it is known as the forest. So a bunch of trees are known to be forest. Okay. So, but tree is important to us. So what is a tree? Tree is a type of graph which is acyclic. So that means there should not be a cycle. And the second thing is it should be connected. So that means it is you are able to find a path between any two vertices. Okay, so these are the two important properties of a tree. Now, what happened for a DFS process and for a BFS process, we can actually get a tree from the graph. Okay, so we can get a tree. We can get a tree using BFS and DFS process from the graph. Okay, so how will you get a tree? So so the vertices of this tree will be the same vertices whatever present in the graph. So for example, here we have our given graph. So suppose this is our graph and we want to we want to find out a tree for this particular graph using BFS and DFS both processes. So what we'll do, first of all, I'll explain for a BFS process with the source vertex 0. So suppose this is my source vertex 0, that my source vertex is 0. And what will, if I apply a BFS scan, what will be the tree we will get? Okay. So for a tree also, we need to figure out what will be the vertices and what will be the edges. Okay. So here we will use the same vertices, whatever present in the graph. So that means here the vertex set will be same as the vertex set of graph. So that means 0 to 9. So we'll use all vertices, whatever present in our graph, to build a tree using BFS process. Now the second thing we need to figure out is the edges, which what are the edges we are going to we are going to consider in our tree. Okay, so but when we consider edges, we need to focus that we should not create a cycle, right? But what happened? This DFS process will take care of that. So that means what you will do, you will take all those edges which were used in your BFS or DFS process. So that means that the building of tree for both methods are actually same. We'll take the same set of vertices. We'll take those edges which are used in our process or in our scan. So edges used in our scan means, so as we just saw in DFS process, we use this particular path. We started with 4, we go to 3, then we go to 5, and then we go to 7 using these edges. So what we'll do, we'll take these edges in our tree. Okay, so once you consider those edges which are used in your BFS or DFS scan, plus the vertices which are there in our graph, this combined thing will form a tree. And that tree is known to be tree obtained by BFS process or tree obtained by DFS process. So I'll go one by one. First of all, we will consider the tree which we can obtain using BFS process. Okay, so set of vertices are fixed.
Ma'am, before we
Yeah.
move forward,
Mhm.
whenever you initiate a BFS or a DFS process, you are
Mhm.
starting with selecting one vertex, whether it is 4 or 0 or whatever. You are choosing
Yeah.
one vertex, and then from the source point, you are going through the process. So
Yeah.
every time you change the vertex, for example, instead of choosing 0 or 4, if I choose 6, then
Hmm.
the sequence will change. The edge
Correct.
sequence
Yeah,
will
sequence
change.
will change.
So from the exam point of view, or technically from any problem point of view, it's
Hmm.
always DFS or VFS is dependent on the
Source
vertex number
vertex.
source vertex.
Yeah.
That is the starting point.
Hmm.
Okay, ma'am. Thank you.
And it's always given in the question that consider this vertex as your source vertex
Source
and
point.
then
Okay.
go with the.
Fine. Okay. Thanks.
So what happened in BFS process? Let's start with our BFS scan with vertex number 0. Okay. So observe how we are building a tree. So we'll start with vertex number 0. Then from vertex number 0, we'll go to the neighbors of 0. So the neighbors of 0 is 2, 1, and 4. So BFS says that explore these all vertices at the same level. So what we will do, we will take an edge which is connecting to 0 vertex to vertex number 2, an edge which is connecting 0 vertex to vertex number 1, an edge which is connecting 0 vertex to vertex number 4. As these three edges are there in our BFS scan. Now BFS says that explore these three vertices one by one. So I'll start with 0 and try to explore 0. But you can, I'll start with 2 and try to explore 2, vertex number 2. But you can observe that there is no new vertex associated to vertex number 2, right? So the only neighbors of vertex number 2 are 0 and 1, and they both got their places in our BFS scan initially, right? So that means there is no other thing we can explore from vertex number 2. So we'll leave vertex number 2, then go to vertex number 1. But same case happened for vertex number 1 too. So that means there is nothing new. We can explore from vertex number 1. So now we'll go to vertex number 4. So from vertex number 4, there are two new neighbors, which is vertex number 7, vertex number 3. Now BFS says that explore these two vertices at the same level. So what we'll do, we'll attach these two vertices, vertex number 3 and vertex number 7, in our BFS tree. So here we are building a tree using BFS process. Okay. So we'll take 3 and 7, which are neighbors of vertex number 4. And these will be at level 3 to us. Or we started with the 0 level. And this is your level number 1. So that means all these 3 vertices will have level number 1. And all these 2 vertices will have level number 2. Now from 3, we can explore vertex number 5, vertex number 6. So that means from 3, I'll say that we go to 5, we can go to 6. And from 7, we can go to 8. And again, from 8, we can go to 9. Okay, so now here, whatever graph we got, so here we got this graph, right? So this particular graph. Now this graph is known to be BFS tree. Okay, so that's how you build a BFS tree.
So there is an edge between 1 and 2. No need
Yeah.
to show it the tree.
Yeah, we don't need to show that edge. So
Okay.
we'll use those edge only which are used in BFS process. This edge is not used in our BFS process, right?
1 and 2, if it is connected, then it will not be a tree, it will be a cyclic.
Yeah, so that's why this BFS processes edge, whatever edge we have considered in
Okay.
that
Got
process,
it. Yeah.
it will take care.
Okay.
Right? So this is the tree we got after applying a BFS scan. So actually what happened, this tree will tell us all information about the graph. So for example, if a BFS tree is given to you, then you can check whatever edge is there in your graph or not. For example, if I ask you, suppose this is our question. Is there any is there possible any edge from vertex number 7 to vertex number 1? Okay. So suppose a question is given to you in which only BFS tree is given to you, and they will ask that is it possible to have an edge between vertex number 7 to vertex number 0, sorry, not 1, to vertex number 0. Okay, so then what will be your answer?
Yes. Yes.
Okay, so the actual answer is no. So let's explore this question, because it's a very I mean, this type of question will be frequently asked in any exam, right? So whatever graph, okay, so let me use this particular space. So suppose I have given you a tree. I have given you a question which says that consider the following BFS tree and answer the following questions, right? So the tree goes like this. So suppose I have vertex number 0, then I have vertex number 1, 2, 3, then I have vertex number some 4, 5, some 6, some 7, some 8, and then I have something like that. Okay, suppose a random question is there in which this particular type of tree is given to you, and they ask that, is it possible to get a graph? Is it possible to get a graph of such a BFS tree in which there is an edge between vertex number 8 and vertex number 0. Okay, so what will be your answer? Let's guess what you guys think. Is it possible to get a tree whose, is it possible to get a graph whose BFS tree will look like this tree, and there is an edge in graph from vertex number 0 to vertex number 8? Because you can observe that here in this particular BFS tree, we haven't used all the edges from the graph. As you guys pointed out, that we haven't used the edge which is connecting to vertex number 2 to vertex number 1, right? So this edge is not there in the graph, and this edge is also not there in the graph. This edge is also not there in the graph, right? This edge is also not there in the graph. So that means there are several edges we haven't used in our BFS tree. But can we guess that is it possible that such type of edge exists in our existing graph or not, just by looking at the BFS tree? Okay, so this type of question is also there in your activity. You guys can go through and check. So what will be your answer here? Can you guess?
No, that's not possible, right?
No, ma'am. No,
No,
ma'am.
right?
Because there is a no edge connecting between 8, 0 and 8 anyway.
Yeah. So another thing is you can observe that if there is an edge between 0 and 8, then 8 will be lie over here, right? So the level of 8 will be 1, because in BFS process we explore it by neighbor, right? So if there is an edge between 0 to 8, the 8 should be here. But in this BFS tree, 8 is lying over the next level of 0. So that means 8 is over at level number 2 and 0 is over at level number 0. So that means it is not possible to get an edge between 0 to 8, right? Is it clear?
So shall we say in BFS tree, there is a possibility of edge if and only if the level is one up or down, one level.
That's correct. Yeah. Yeah, it is possible to get such type of tree. So that means whenever two vertices are separated by 1 plus level, so that means 0 to 2 or 1 to 3 type that, then it is not possible to get edge between those vertices. Okay, so the reason is obvious. If there is an edge, it will be a level above. Okay. So this is all about BFS tree. Is there any doubt how to get a tree from a graph, or how to judge that this particular is a BFS tree or not? Something like this.
So we can have multiple trees from the graph, right? It depends on the choice of the vertex to begin with, right?
Correct. We can have multiple trees related to a graph. Okay.
So in the question, if the tree is not given, but the graph is given and asked to find out the edge between 0 and 8. In that case, we have to first convert the graph into a tree.
No. If such a
And-
graph is given, then just by looking at the graph, you can answer, right?
Yeah, okay.
Then it's just look at the graph, is there is an edge or not, then that's all.
Okay.
Okay.
Is there any directed and undirected?
Sorry, your voice is not clear.
Am I audible?
Yeah, you're audible, but your voice is a bit low.
Bit low. Now,
Yeah.
will it be an undirected or directed like that? Is there any strings?
See, it doesn't matter it is an undirected or directed. See, in directed graph, you just have to respect the direction. So whatever direction is given, you have to consider those edges only. So we'll move to DFS numbering. In DFS numbering, we'll tackle the directed graph. So in that, you will observe. Okay. So you can apply both methods for directed and undirected graph. The only thing is in directed graph, you have to respect the direction. So for example, if the direction of this particular edge is like this, then you cannot go from vertex number 4 to vertex number 0, right? So you have to consider only 3 and 7 as the neighbors of vertex number 4. Okay. So now let's go to DFS numbering, which is I think in the next lecture. Yeah, so this is application of BFS and DFS. So here first we'll recall what is a DFS numbering, and then we'll go to their applications. So it just says that DFS automatically compute the reachability of graph, all those things we know. Now here the connected, disconnected components also you guys can just look at the graph, just look at the tree and you can answer. The component number is also, so what does a component number means? So as you apply your DFS and BFS process, you will give a component number to each vertex, whatever vertices got scanned over the first scan, right? So that means, for example, what is that component number is called? So what is a component number? So actually we want to judge that how many components are there in our given tree. Okay. So for example, this is our one graph. The two blocks are given to be as a single graph. So this is our single graph. So in this graph, you want to judge how many components are there. So component means you can take as you'll collect all those vertices which are connected to each other. make it as a subset and collect all those vertices which are connected to each other. For example, in this particular graph, if you take 0, 1, 4, 8, 9, this will be your one component. And if you consider single vertex number 5, this will be your second component. And if you consider the set of vertices like 2, 3, 6, 7, 10, and 11, since they all are connected to each other, right? 2 is connected to 7, 2 is connected to 6. We can move from 2 to 11 too, right? Go up via this, via by vertex number 7. So this is another component, the third component. So this is the meaning of component. Component means collect all those vertices which are connected to each other. That will be your one component. So a connected graph is in which we just have one component, right? Because if it is a connected graph, you can reach from any vertex to another vertex. So you will have just one set. So that is
So
a connected graph.
path can be called as a component, man. That's what you're saying. Because if it's
Not exactly path, because this is not a path 0, 1, 4, 8, 9. But path means you will collect all those vertices which are reachable by a path,
okay.
right? That means 0 and 9 can be connected via a path. So we'll take 0 and 9 into the same component.
Okay.
Okay, so component like you can observe like a pieces, right? So there are 3 pieces of this graph. So you can break down this graph over 3 pieces. Of the first piece is this piece, the 0, 1, 4, 8, 9. Second will be the only singleton 5, and third will be this particular piece. Okay. So now using DFS or BFS method, we can actually find out that how many components are there in the graph. So what we will do, we'll apply BFS and DFS scan over and over. For example, in this graph, so let's start with the BFS scan. So if you apply BFS scan from vertex number 0, what we will do, we'll go to vertex number 0, explore its neighbors, go to their neighbors, right? So this will be your first scan. So, but if you apply one BFS scan, you can visit only 0, 1, 4, 8, and 9, right? You cannot visit any other vertex if you start with vertex number 0. So that means it is possible to visit these vertices using a single BFS scan. So what we will do, since we have used one BFS scan for this particular component, and so we'll give a component number starting with 0. So that means for visiting every vertex of the graph, how many times we have to apply our DFS or BFS process, that number will give us the component number for the graph. For example, if you want to visit each and every vertex in this particular graph, then you need to use BFS process at least 3 times, right? First time, we will apply our BFS process from vertex number 0. Then from vertex number 0, we can visit vertex number 1, we can visit vertex number 4, we can visit vertex number 8, we can visit vertex number 1. Now you have to apply another BFS scan from starting vertex number 5. So here we will apply the second BFS scan. So from 5, we cannot go anywhere. So that means we have to use another BFS scan. So now we will start another BFS scan, the third BFS scan. So using the third BFS scan, we can visit these remaining neighbors. So that means for visiting each and every vertex of this type of graph, we need to apply BFS scan 3 times. And whatever this number is 3, this will give us the number of component present in the graph. Okay, is that clear? Am I moving too fast?
No, ma'am.
Yeah, because this
So
component number is just you can look and guess.
basically, these are levels, right, ma'am? Each component is one layer.
No, levels are something different. For example, if you start one BFS scan from 0, this will be your 0 level, right? 1 and 4 will be at level number 1. This will be level. So
Okay,
these are
okay, okay.
component numbers. So component number means in a single BFS scan, how many vertices you can explore. Those all vertices will have the same component number.
Okay, okay. It's not level then. Okay.
Yeah, it's not like that.
That means you can say trees, number of trees in the graph.
Yeah, that's also correct. Number of trees in the graph also.
Right, right.
How many trees you can construct.
But here, each tree will have only one level. because it's a BFS, right? You only go one level down every time. You don't go beyond that, right?
See,
In-
level is given to each and every vertex, right? So, for
Oh.
example, what is the level of vertex number 1 in your BFS process? So that will be a
Okay.
question, right? So level is not assigned for an entire graph or for a tree.
Sure. Okay.
Okay. So this is all about component numbers. Now I'll start with how to compute a cycle in a graph. Okay, how to find out the cycles in any graph.
Ma'am, cycle can be present in a tree.
Cycle is present in any what?
Cycle can be present in any tree. Means it is
No,
possible.
in a tree we cannot, we can't find cycles.
Ma'am, then
Because
how?
see, tree means what? Tree is only acyclic connected graph. So that means we need a graph in which we don't have any cycles.
Then, ma'am, in the previous section, how can we say that that is a tree? There was cycle and
See, this is the single component is a tree, right? No, it is also not a tree because we have a cycle here.
cycle. Yes.
Yeah, right.
Okay.
1 second.
Madam told how many trees can be constructed in this graph. That is what you told, no, madam. See, when I
Yeah,
told
how many trees? How many trees?
yeah,
So you can
when I
construct.
told the component is
Hmm.
so you can say synonymous to number of trees you can construct.
Yeah, correct. That's
So
true.
the tree can be constructed using BFS or DFS. That is left to the person. But
Yeah.
using that BFS or DFS, how many distinct
Trees we are getting.
trees you are getting? So first tree will be component 1, second tree will be component 2, third tree will be component 3.
Yeah.
So it's something like that.
Yeah. So that's correct, because ultimately what the number of tree depends on how many times you need to apply BFS and DFS to entirely visit the graph, right? So we need to apply 3 times a BFS or DFS process to visit each and every vertex of this particular graph. So that number is our component. So that many component will be present in the graph. Okay. So now how we can judge the cycles in a graph using BFS / DFS. Okay. My screen is visible?
yes, ma'am.
Yeah. So here the question is, how can we spot the cycles in a graph? Using BFS / DFS. Okay. So actually, we will use these. So this question can be categorized for both. So that means there are 2 different answers for directed graph and undirected graph. So I'll start with undirected graph. So suppose we have an undirected graph. Suppose we have an undirected graph. Okay, so undirected graph means that graph with no direction specified. So an edge can be thought as 2 directed edge, right? 2 directions edge. So that is an undirected graph. So in an undirected graph, those edges, edges which are not present in BFS or DFS tree will construct a cycle. So that means in undirected graph, the answer is very easy. What we will do, we will take the BFS or DFS tree, and whatever edges are there which are not used in our BFS or DFS tree, those edges will create a cycle. Okay. So now here you can observe as we are in this particular graph. So here we, if you consider the BFS tree of this particular graph, this whole graph, so there will be 2 scans we need, but suppose we have only one single graph. So suppose this is your graph 0, 1, 4, 8 to 9. Okay. And for this graph, if you apply a BFS process, then what will be your BFS tree? So the BFS tree, so suppose I'll start with vertex number 0. So I'll start with vertex number 0. From vertex number 0, I'll explore vertex number 1 and vertex number 4. So 1 and 4 got explored. From 4, I'll go to vertex number 8 and vertex number 9. Vertex number 8 and vertex number 9. So observe what are those edges which are used in this particular tree. So we use this edge to connect 0 and 1. We used this edge to connect 0 and 4. We used this edge to connect 4 and 9. This edge for 4 and 8. But we haven't used this particular edge. But what is happening? This edge is creating a cycle in a graph, right? So this edge is a reason for we are getting a cycle in this particular small graph. So that means in an undirected graph, those edges which are not present in a BFS or DFS tree, those edges can cause the cycles in the graph. Okay, so for an undirected graph, the answer is very easy. We'll select all those edges which are not there in a BFS or DFS tree. Is that okay? Is that okay for everyone?
Yeah, ma'am.
For that, we need to have both graph and tree, right, to decide this. If we have
Yeah,
only,
correct.
if we have only either graph or tree, we cannot decide that. Because
Yeah, we
there
need
are
both
charts
things.
of an edge from 0 to 8 or 0 to 9 also.
Right,
Or
right.
1 to 9.
Right, right.
Okay.
Okay. So now the thing is for what happened for directed graph. Okay. So for directed graphs, we use only DFS methods, and using DFS method. So for directed graph, we will use DFS method to put a DFS numbering over the graph. And using this numbering, we will judge for a cycle. Okay, so now let's go to what is a DFS numbering. So what is the motive of DFS numbering is to judge the cycle present in a directed graph, or is it possible, or to judge what are those edges which can cause the cycle in the given directed graph. Okay, there are other uses of this particular DFS numbering too, but we will just focus on the only purpose to find out the edges which are creating the cycles. Okay. So you guys know what is a cycle is and all these things, simple cycles. Okay, so now let's go to DFS numbering. So yes. So here what we will do, so suppose this is your graph and you want to give a DFS numbering to this particular graph. So what is a DFS numbering is, so for any vertex, we will assign 2 numbers. So suppose you have a vertex U. So for this vertex, we will assign 2 numbers. One is the pre number and another one is the post number. Okay. So what is a pre number? So again, what are these numbers is? So these numbers are just counting. So that means we have to count the steps in which step we are entering a vertex and on which step we are getting out of that particular vertex. Okay. So this pre number and post numbers are just a part of counting. So that means we will use the counting here. So we'll start with 0, 1, 2, 3, 4, 5, 6 and so on. We won't break our count. But here, whatever numbers we have, so that means we have 0, 1, 2, 3, 4, 5, 6, right? So you'll assign this number as a pre number or post number to a vertex. It depends on the nature of BFS or DFS process. DFS process. So these counts or these numbers, this particular number 0, 1, 2, 3, 4, will categorize over 2 numbers, the pre numbers and post number for a particular vertex U. So what will be a pre number for a vertex U? So pre number is that count in which we are entering in this particular vertex. Okay, so that count on which we are entering or visiting this vertex. Okay, so what is a pre-number means? Pre-number will be that particular count in which we are entering into this vertex or visiting this particular vertex. And what is the post count? Post count means that number, that count on which we are backtracking this vertex. Okay, backtracking or leaving this vertex. So you can assume that the backtracking means just leaving that vertex, right? So we'll backtrack to that vertex which are giving us a new information. So again, I'll repeat, this pre-number and post-number are nothing but a part of a counting. So what is a counting means? So we are doing some counting here to strategize what are the steps we are using and how these steps are going, right? So for a vertex, we will assign two types of count. One is the pre-number, another one is the post-number. So what is a pre-number? So pre-number will be that count on which we are entering into a vertex. What is a post-number? Post-number will be that count on which we are leaving that vertex. Okay, so let's understand that particular thing with an example. So suppose I'll apply a DFS process for this particular component using considering 0 as my source vertex. Okay, so as I told you that for a vertex we assign two numbers. One is the pre-number and another one is the post. So whatever your source vertex is, that vertex will have a pre-number 0. Okay, so this so here we are using our first BFS scan, first DFS scan. Okay, so it is possible to apply more than one DFS or BFS scan to each graph. Okay, so when so why we need more than one DFS scan? Because see here there are two components. So it is not possible to visit each and every sorry, there are three components actually. So it is not possible to visit each and every vertex using a single BFS scan only, single DFS scan only. Okay, so that's why we need more than one DFS scan. So as we start with our first DFS scan, we will give 0 pre-number to vertex number 0. Okay, so now what will be the next step from vertex number 0? Which vertex we will visit now?
We'll go to 1.
Right, so we'll go to 1. So what is happening here? We are entering into vertex number 1. So this will be our 1 plus count, right? So here we are at 0 count. Here, whatever thing we are doing, that entering will got count number 1, right? So what we will do, we'll assign pre number 1 to vertex number 1. Okay, so we will assign pre number 1. So what we will do, we will assign a pre number 1 to vertex number 1. Okay. Now after this, after vertex number 1, what will be our next step in DFS process?
We'll backtrack to 0.
Right, we'll backtrack to 0 because there is nothing new from vertex number 1.
And
Now,
assign post number to 1 to 0.
Right, correct. So now we will assign a post number to vertex number 1 as 2, right? Because as I told you, this pre and post numbers are a part of count. So we won't break our sequence. So as we use 0, we'll go to 1, we'll go to 2 now. So I'll assign post number 2 to vertex number 1 and go to vertex number 0. Okay. But on vertex number 0, what will be your next step now in DFS process?
Go to 4.
Go to vertex number 4, right? So here we are not leaving this vertex number 0 from our DFS process, right? We backtrack to vertex number 0, but we haven't leave this vertex number 0 from our DFS process. We need this 0 again to go to vertex number 4, right? So that's why we won't assign a post number here, right? We'll go to vertex number 4, assign a pre number. Now what is our count? 0, 1, 2, and now 3. So I'll assign a pre number to vertex number 4 and then go to the next step. Here we are not assigning a post number to vertex number 0 because we need 0 in our DFS process. 0 will be there in our stack of suspended vertices, right? We haven't backtracked it yet. So that's why we won't assign a post number to vertex number 0. We will assign a post number to any vertex only when we backtrack from that particular vertex. As we backtracked from 1, but we haven't backtracked from 0. That's why we won't assign a post number to vertex number 0. Okay. So the next thing will be, we will enter to vertex number 4 with pre number 3. Now what will be the next step in DFS process?
We go to 8 with pre number 4.
Correct. So since here we are entering into some vertex, we will assign a pre number. And as we maintaining our count, so the count is 3. So now the next number will be 4. So we'll assign a pre number 4 to vertex number 8. Now from vertex number 8, we'll go to vertex number 9 with pre number 5. Now here from vertex number 9, we don't have anything new. So what we'll do, we'll backtrack. So as we backtrack, we will assign a post number. But since pre number and post numbers are count, we won't break our counting. So here the 5 is there. So we'll assign the post number 6 to vertex number 9. Then go to vertex number 8. But again, from vertex number 8, there is nothing new. We can, there is no unvisited vertex from vertex number 8. So we have to backtrack from vertex number 8. And whenever we backtrack, we will apply a post number. So we'll apply a post number. So the count is 6 to 7. Then we'll go to vertex number 4, apply the, indicate the post number 7 to 8. Then go to vertex number 0. Now here from vertex number 0, now there is nothing new we can explore. So now we will apply a post number to vertex number 0, which is 9. Okay. So now here, whatever counts we get, these are known to be DFS numbering. Whatever numbers we have assigned for each vertex, that is known to be a DFS numbering. Okay, is that clear? So you guys can apply, we have 6, 6, 7, 8, and then 9. But see, here, only one part of this graph is done. There are 2 more components. So what we'll do, we'll apply second scan of DFS from either this component or this component. Now here again, in the second scan also, you have to give pre and post number. But again, these pre and post numbers are counts, so we won't break this particular count until and unless we visit each and every vertex. So that means if you start your new new DFS scan from vertex number 5, you will give pre number to vertex number 5 after 9 to 10. And you will, since there is nothing new from vertex number 5, you will leave vertex number 5 at count of 11. Okay, so that's the thing we need to do. Since they have chosen 2, so that's why instead of 5, we have 2. So we will enter 2 with count 10. So that means the pre number will be 10. And then we do the same process over here. Okay, so anyone want to volunteer? What are the numbers we will give? What are the numberings we will give for this particular component?
So 2 will go to 3.
2 to go to 3.
And 3 will get pre number as 11.
11, right?
And 3 will go to 7 because 6 you cannot reach, so it will go to 7.
Right. 7.
And 7 pre numbering will be 12.
12, correct.
So from 7 you can go to 10 because 10 and 11 the least number is 10, so it will go to
Right.
10. The pre number will be 13.
13.
So from there you cannot go anywhere, so he has to backtrack. So
Sorry,
he will
this
go
is
back
10. This is 10.
10. Yeah, 10. So from 10 it will backtrack. So it will get a pre
From
numbering.
10, you can go to 6.
6,
Oh,
right?
6 you can go, right? Oh, okay.
Right. With pre number 14.
Pre number 14.
Now from 6.
6 you can go to 2, I think, then in that case. No, 7.
Yeah, nothing new is there from 6, right? This is visited,
Yeah,
this is
7
visited.
2, 3 is
Everything is
visited,
visited.
7
So
is
we have to
visited.
backtrack.
Backtrack. So from 6 it will be 15. Post number will be 15, 16,
16,
17,
17.
18, and then the 2 will get 19.
11 is there.
We have not visited
From 7,
11. You can
from
go
7
from
it goes to
7 to
11.
11.
Yeah, sorry. Correct.
From 7 you have to go to 11.
Yeah.
Yeah. So now 7 won't get the post number. So we'll go to 11 with count 16 with 17, then 18,
17,
then 19, 20,
Yeah,
21.
21. 21. Then if you add 5, then you will get to 21 and
22,
22,
23.
21, 23. 23.
Okay. So this is our DFS number. Okay. So it is clear, na? Any doubt?
No, ma'am.
Okay. So now the thing is, okay, so now we have this pre number and post number, but how can we judge the cycles in a graph? So the answer is we will classify edges, the tree edges, whatever edges we have. We will classify the non-tree edges. Non-tree edges means those edges which haven't been used in our particular DFS. For example, from going 2 to 3, we have used this edge, then we have used this edge, then this is going to 6, then this one and this one. So that means these edges we have used, but these round one we haven't used. So what we will do we will give a specific names to these edges. Specific names to these edges. 。 Okay, so we'll give whatever non-tree edges are there, we will give specific names to these non-tree edges. And using these edges, we will classify which edge will cause cycles or not. Okay, but since it's an undirected graph. So in undirected graph, as I told you, that whatever edges is there which haven't been used in our DFS and BFS scan, those will create a cycle, right? So here it is obvious, since this edge haven't used and it is also creating a cycle. This edge haven't used, this is also creating a cycle, right? And these two edges haven't used, so these two edges both combiningly creating a cycle. Okay, and also if not combiningly, we can just simply observe that this edge is also creating a cycle. So whatever non-tree edges are there which haven't used in our DFS tree, those edges will create a cycle. Now let's go to in case of directed graph, right? So in directed graph, we will give these non-tree edges as some special name, and those names are forward edge, backward edge, and cross edge. So let me
What is
go
the
to
use
the
of
next.
this numbering, ma'am? Ultimately, after this exercise of numbering, pre-number and post-number, what is what is that we are going to derive out of that?
Yeah, so we will find out
Will
those edges which are creating cycles actually in a directed graph.
okay.
Yeah, in
Sure.
a directed graph, we will use.
So we will use that in the.
Not in undirected graph. Undirected graph, it's easy because whatever edges is not there in your DFST, those will create a cycle. Okay, so this counting part I'm leaving because it's just the theoretical part, how many things we need to use. Okay. So now here. Yeah. Is there any doubt? No. So now what we will do, first of all, we will find out the DFS numbering for this particular graph. But before that, let's classify what are the forward edges, what are the backward edges, and what are the cross edges. Okay. So the forward edges are those edges which will grow in the direction of tree. Okay. So those edges which grows in the direction of DFS tree. So that means we have a DFS tree, and in that particular DFS tree, whatever non-tree edges. So here we are classifying non-tree edges. Okay, non-tree edges. So, so the thing is, we have a graph. So from this graph, we are extracting one tree, which is known to be DFS tree. And we are classifying those edges from this graph, which are not present in our DFS tree. Okay, non-tree edges. So we are classifying these edges into three categories: forward edges, backward edges, and cross edges. Forward edges are those edges which are growing in the direction of DFS tree. Growing in the direction of DFS tree means, suppose your DFS tree is growing in the direction of this one, right? So whatever edge is there in the given graph with the same direction, right? So in the same direction. So suppose I'll take one simple example. So suppose this is our DFS tree. 1, 2, 3 is there. 4, 5, 6. Suppose this is our DFS tree. And if there is an edge from which is connecting 0 to 4 in the same direction. Okay, in the same direction as the tree goes, that edge is known to be forward edge. Okay, and the opposite of this is our back edge. Back edge means those
Can you
edges
please
of.
repeat it? You
Sorry,
have
what?
drawn the tree, right?
Sorry,
Which is
what?
the graph for, can you please repeat it? The forward edges?
Yeah. So forward edges are those non-tree edges. So here the red one is the DFS tree.
Okay, of the graph which is
For
Yeah,
above.
the
of
given
the
one, no?
any graph. Yeah. Sorry,
For the
what?
given one, madam. This is
No,
for
no,
the
no,
given one.
not the given one. I'm taking a
Okay,
random
okay.
example.
Okay.
Okay. So suppose this is a DFS tree of any graph, and in this graph there is an edge from vertex number 0 to vertex number 4, 2. Right, which haven't used in this particular DFS tree. Then this edge will known to be a forward edge. Okay, so ultimately those edges from the graph which haven't used in the DFS tree and which are respecting the direction of tree. So that means here the direction of tree is downward, right? So this edge is also going downward. So such type of edges are known to be forward edges. Is that okay?
But it should not be used in the
It should
tree.
not be used in the DFS tree. They
Okay.
are strictly non-tree edges.
Okay.
Okay.
So to identify the forward edges, we should have both graph and tree.
Yeah, correct. We should have both graph and tree, or else if you have DFS numbering also, then also you can judge. So how we can judge, I'll come to that. But first understand what are the definition of these edges. Okay, so what is a back edge? So back edge is just an opposite of forward edge. So in place of in the direction of tree, we need an opposite direction of tree. So for example, in the given graph, there is an edge from vertex number 4 to vertex number 0, right? Which is opposite of the direction of DFS tree. Now this type of edges are back edges. Is that okay? Forward edges and back edges? Yes, no?
Yeah, okay.
Okay, right?
Yes, ma'am. Yes, ma'am.
So forward edges
Yes, ma'am.
means those non-tree edges which are growing in the direction of tree. Backward edges means those non-tree edges which are growing opposite of the direction of tree. Okay. Now what is a cross edge? So cross edge will be that edge which is connecting, which is in between the two branches of tree. Okay. So for example, if there is an edge between the vertex number 4 to vertex number 5, then this type of edge is known to be cross edge. Right? Which are among the what you will say, among the two branches of tree. Right? So those type of edges are cross edges. If there is an edge between 5 to 6, that's also we can say as a cross edge, because that edge is among the two branches of tree. Okay, so cross edge means those edge which are among the branches of tree.
Can we say which are at the same level?
Yeah, but it is possible to be at different level too. For example, 4 to 2, right? So 4 and 2 are of different level, but if there is an edge between 4 to 2, that edge is also known to be a cross edge. Okay, so it's better to say among the branches. Okay.
So forward and backward edges ought to be in the same branch.
Yeah, forward
Only
and
cross
backward
edges-
edges, yeah, they should be in the same branch. Yeah, that's a good point. So forward edges and backward edges should be in the same branch. Okay, so the cross edges are those edges which are among the two branches of tree. So now the thing is, only backward edges will create a cycle in a directed graph. So let's explore it. But I'll again recall what are the forward edges. Forward edges are those non-tree edges which are growing in the direction of tree. Backward edges are those non-tree edges which are growing in the opposite direction of tree, and both should be in the same branch. And the cross edges are those edges which are connecting two branches of a tree. And again, these three are non-tree edges. So that means they haven't used in a DFS tree. Okay, is that clear? Any doubt in these three edges? Okay, now how we can judge this forward edges and backward edges and cross edge? But first understand why only back edges will create a cycle. Okay, so the fact is only back edges will create a cycle. Okay, so only back edges will create a cycle. So the thing is, suppose your tree is growing in the same direction. So suppose this is the direction of your tree. And if you consider the forward edge, okay, so if you consider the forward edge, then that forward edge is also growing in the direction of tree. So if we have all edges in the same direction, then it is not possible to create a cycle in a directed tree, right? For a cycle, we need two edges in the same direction and at least one edge in the different direction. Then only you will create a cycle, right? In this case also won't create a cycle, but for example, like this, we have this direction, then we have this direction, and now we need an edge which is opposite of these two directions, right? So if we have forward edge, for example, here this yellow one is a forward edge. So then forward edge always grow in the direction of tree. So here, because we have all edges in the same direction, a forward edge cannot create a cycle. But if we look at the backward edge, then we have two edges which are growing in the downward direction, and we have one back edge which can connect the endpoint and the starting point of these two edges. So here we can get a cycle, right? We can get a cycle. So that's why in a directed graph, only back edges will create a cycle. And similarly, you can argue for cross edges. In the cross edges, we have two edges in this direction and we have a one cross edge. So here also it is not possible to create a cycle because of the direction issues. So these two will have the same direction and this is just connecting this two different directions. So here also we don't get a cycle, not a cycle. Okay. So is the reason is clear why back edges only create a cycle?
Okay, cross, why you are saying cross edge will not create a cycle? No? Because it's a cycle, no? It's coming here, coming,
No, it's
going
coming
to the
here.
right and
We are
then,
going
oh,
here, but we cannot go back, right?
okay.
Right? Because of the direction. So here also not a cycle, here also not a cycle. But
Okay,
here,
it's a directional graph. Okay.
yeah, it's a
If
directed graph.
if you look at a non-directional graph, then the other one is true. Okay, understood.
Right, because in undirected graph, it's easy to spot a cycle. Just
Yeah,
take all
correct.
those edges which are not there in directed.
Correct.
But in directed graph, only back edges will create a cycle. Okay. So now how we can judge forward edge, back edge using the DFS number. Okay, so for that we have a very simple formula. Okay, so this is, we come to topological sorting now. Let me see. So it's simply we need to consider which interval is contained in which interval for the given graph. Let me check the other PDF. Okay, so I can explain by the given graph only. Okay, so suppose you have a vertex u here and you have some vertex v here in a DFS tree. Okay, in a directed graph DFS tree. Directed graph DFS tree. Okay, and you need to judge using the pre number and post number. If there is an edge from U to V in the original graph, is that that particular edge is a forward edge, cross edge, or not, or back edge. Okay, so what you will do, you will take care of the intervals. So for example, here, suppose that, let me draw that. Okay. So suppose in your DFS tree, you have two vertices. One is vertex number u, another one is vertex number v. In between, you have some structure of tree, a directed structure, right? So suppose some vertices are there, something is there, but you have some directed structure over here. Now, there is an edge. There is an edge between u to v in original graph. Okay, so that means there is an edge from u to v in your original graph. Okay, so but by the picture you can say that this is a forward edge, but suppose it's not given, the TFS tree is not given to you, but just only pre number of u. So here we have given pre u, post u, and pre v, post v. Okay, so then how can we judge that this particular edge from u to v is a forward edge, backward edge, or a cross edge? Okay, so there are three things. So the first thing is, suppose that this particular interval, that is pre-u and this post-u, this particular interval is actually containing the interval pre-v, post-u. Right? Because this pre-u and post-u are just numbers. For example, this number is 0, 14 and this number is something 2, 5. So suppose this is the case is given to us. Okay, so in that case, what we can say, so in this case, we can say then the edge from u to v will be a forward edge. And why is this so? because from the numbering you can observe that suppose a pre-u is 0 and pre-v is 2. So this pre-number will say that, okay, you will come at the upper place or at the starting of the tree, and v will come at the bottom of the tree, right? And 2. And since 5 is less than 14, it says that this vertex number v get over first or before the vertex number u get over, right? So that means this u and v will be in the same branch, and the vertex number v will be at the what you can say, at a little downer than the vertex number u in our given DFS tree, right? And here, if we have an edge from u to v, it's obviously a forward edge. Okay, so the fact says if we have just a pre number and post number, and if the pre-u and post-u, this interval contains the interval of pre-v and post-v, then the edge from u to v is a forward edge. Okay, is that clear?
Yeah. Ma'am, will there be a case where this 14 and 5 can be reversed? Is that scenario is possible?
14, yeah, it is possible if they both have over the different branches.
Okay.
Right. So that's why we need the strict containment here, strict or less, yeah, right? This type of containment.
But we are not talking about in between branches. We are talking about within the branch. Okay.
Within the branches. So if this scenario happen, and if there is an edge between u to v in the original graph, that graph will be your forward edge. Okay. Similarly, we can classify the backward edge. Okay. Similarly, if the opposite of this is true, so that means if pre-u comma post-u is contained in pre-v comma post-v, is contained in pre-v comma post-v, and there is an edge from u to v. See here, I am always taking an edge from u to v. Okay, and I am just reversing this particular property, that now the containment is reversed. So in this case, what is happening? So in this case also, since the direction is from u to v, but the containment is reversed, we can say that this will be a back edge. Okay, because this containment will show us that now v will be at the upper place and u will be at the lower place. Okay, and over the same branches, since the containment is there. Okay, so here we have in between some vertices, this type of scenario is happening, and we have an edge from u to v. So now this will create a back edge.
Can you please explain with some numbers?
Yeah, sure.
And post.
Yeah. So suppose the same thing has happening. So suppose this is some 8 and 10, and suppose this is some 13 and 12. Okay. So now what is happening here? U has pre number 8 and post number 10, and V has pre number, oh, sorry, this 13 won't work, no? So I'll take 6, right? Because containment should be here. 8, 10 can be contained in 6, 12. Okay, so here what is happening? This pre-V has a lesser pre-number. This V has a lesser pre-number. So it has a lesser pre-number means this vertex number V will be at a little bit higher place in our DFS tree, right? And after this we have some vertex with pre number 7. Then after that we have some vertex with pre number 8, and that vertex is our vertex number 8, right? And after doing some things, we reach at the vertex number u, and we got a post number 10. And after that, there will be some vertex in between which have post number 11, and then at the end we have a post number 12. Okay, so this containment shows us that the vertex number the vertex number v is at a little higher place in our DFS tree, right? So that means this vertex number, this particular edge from the vertex number u to vertex number v is growing in the opposite direction of tree, right? So this is our direction of tree, and it is growing in the opposite direction of tree, so that's why it's a back edge.
But in the earlier example, in the forward, if you look at the numbers are slightly different. So here is 8, 10, 6, 12.
Yeah, so here containment is different, right? So whatever bigger interval is there, but that vertex will be in the upper position. So here u has the bigger numbers, right?
Okay. Yeah.
0 and 14. V has the smaller numbers 2 and 5. So that's why in this case, u will be at the upper place and v will at the bottom, right? And here we have the same direction edge.
No,
Okay.
in this the first case, the 2 and 5 were within 0 and 14.
Yeah, that's why.
Whereas in this case, 8 and 10, 6 and 12.
Yeah,
So
6
it's
and 12.
only one number is between and the other one is outside the. Okay.
Okay, is that clear? This particular thing can be a little confusing, but you need to understand that what if this type of situation is there, then which vertex is lying at the first place and which is in the bottom of the tree. Okay, so if you get that, then it's easier to classify the edge. Okay, so now the third thing is if these two intervals are disjoint. Disjoint means if there is no containment. So if these intervals are disjoint. Disjoint means suppose for a vertex number u, we have an interval like 1 to 4. And for the vertex number v, we have an interval like 3 to 5. Okay, so now you can easily see that this is not contained in this one and this is also not contained in this one. So here we have a disjoint interval. So in this case, if there is an edge between u to v, so if there is an edge between u to v, then it's a cross edge. And how is this so? So for example, you have your vertex number u here with pre number 1 and post number 4, right? And you have a vertex number v here with pre number 3 and post number 5, right? So now from reaching post number, yeah. Any doubt?
The pre number of 3 is contained in the U, the intervals of U, right?
Yeah, this is pre-u, this is post-u.
Yeah, but the example that you've given here, the pre number of V is contained in
Okay.
the post in the
Yeah,
intervals of
yeah. Sorry. So I want to write 0, not 0. I want to write this as 3 to 7. No, the initial one was also correct, no? 2 is here, but 2 is not here. So they are. So disjoint means one is not contained in another one. So we have 1 to 4, and then I have 3 to 7. This is 3 to 7, right? So none of them is contained in another one. So they are not containment is there, right?
But in the second example also you have the similar numbering. Now, if you go back to the second example, that is backward, I think. Yeah, if you
Yeah,
see
but
here,
here
six is between 8 and 10, but 12 is outside, which is exactly same as what your example, the third example.
No. See here, what is happening? See here, this is 6, this is 12, and
Yeah.
this is some 8, and this is 10. So this interval is contained inside the bigger interval.
Okay,
Correct? This containment is correct.
Hmm.
Right? Observe that this is a part of an interval. 6-12 is one interval, 8-10 is another interval.
Okay.
And so the
Right.
entire interval should be contained in the given interval.
Yeah. Entire interval should be contained in the another one.
Okay.
Right. So here this interval is not contained in this interval because this
There
this
in the
part is
interval, but not present in the
right.
Overlap is there, but it is not contained in one within the other. Okay.
Correct. So not contained in one.
Ma'am, can you go back to the first example just for a second? Just want to confirm.
Yeah.
First example. Here 0, 14. So 2 and 5 also are contained. Okay, understood.
Yeah. 0, 14 is there and 2 and 5 is there.
Yeah, sure. Right.
Containment is.
Yeah.
Okay. So now here they are not contained in any one. So that means the pre-u post-u is not contained in pre-u post-u and the vice versa is not there. So here we can say that they are a little bit disjoint, or disjoint is not the correct word, but let's say they are a little bit disjoint, right? So
no containment.
No containment. So it's better to write no containment because disjoint means entirely disjoint.
Yeah.
That's why I was thinking like the two intervals have some intersection of the elements. So disjoint might not be the right.
Okay, so there is no containment. So now here what is happening? So suppose U has pre number 1, U has post number post number 4. So for reaching out from post number 4 to post number 5, we need to go, and since here there is difference between pre number, right? So if you go above, the pre-number will decrease, not increase, right? So that means whatever vertex is lying over here, that vertex will have pre-number 0, right? Since we know that the direction of graph is downward. Is that okay? Clear? So suppose some W is there with pre-number 0. Now from this pre-number 1 to pre-number 3, if I want to go, what I need to change? I need to change, okay, so this is also not possible. So actually disjoint is correct. I was forgetting. We need entirely disjoint. Because then only we can go from post number 4 to post number 6 here. And
maybe you
this
can go
vertex will
from
be in the another branch.
yeah, so maybe you can go from 1 to 4 and then 5 to 7 or something of that sort, right? So should be two different sets.
Yeah,
I mean,
but
two
we
different
cannot
intervals.
see pre-number cannot be lesser than the post number of this branch. Because again, since they are counting, so they will in the increasing order. So if I have a count of 4 in one branch, the count of vertices in another branch will be bigger,
More than the
more than the count.
post number.
Yeah. So that's why here
Yeah.
disjoint was correct.
Yeah,
So
disjoint,
we
but the
need
numbering
entirely disjoint.
number has to change. So it has to be 5 and 7, maybe.
Right.
Instead of 3 and 7, you make it 5 and 7.
So if you make it 5 and 7, now this disjoint is correct.
Yeah.
Okay. So then only we will change a branch. So now here the pre number will be 5, here the post number will be 7. So which will indicate that these two vertices are on the different branch of a tree. So if there is an edge between these two vertices, that edge will be your cross edge. Okay. Let me recall quickly. So what are the cases
So
we
how
use?
do you differentiate between that disjoint and cross edges?
See, if there is an edge between U and V, since U and V are of different branches of tree, right? This is one branch of tree, this is another branch of tree. So any edge between the branches of tree is the cross edge, right? And we find out that these two vertices will be situated over the different branches because of the numbering.
And pre and post numbers for disjoint also it is the same overlapping, no?
No, it's not now.
It's not overlapping, entirely different. Okay,
yeah,
okay, okay.
entirely. Okay. So let me recall. So if so again, I am fixing the direction. There is an edge from U to V. Okay. So first fix, there is an edge from U to V. Okay. So the first case is if the interval pre U comma post U, this contains the interval of pre V comma post V, then in this case we have a forward edge. The second thing is if the interval of pre-u comma post-u, if this is contained in pre-v comma post-v, then it's a back edge. And only back edge will create a cycle. And the third case is when they are disjoint. Okay, so in this case, we have a cross edge. Okay, and only back edge will create a cycle.
Ma'am,
Is that okay?
Yeah, one question, ma'am. In both case 1 and case 2, you are using equal to. So how can it be possible that
No,
equal to in both cases?
Yeah, it's not equal to. You can forget about equal. Actually, I'm habitual of writing that sense. Because if it is equal, then both vertices are at the same place.
Yeah,
That means U is equals to V. So, okay, is that clear? It's a little confusing, but you just if this is a little confusing, how to just understand the process that why this result is true. Otherwise, you can just mug it up and find out which one is a forward or backward edge, right? Okay. So now this is a one topic. Any doubt in this one? Forward edge, back edges? Any comments? Now the next topic is topological. Yeah. Anything? So now we need to understand what is a topological sorting means. Okay. So what is happening? Uh, we have some tasks to do. For example, in our case, we understand that we need to set up an office place. So for setting up an office place, we need to do different types of tasks. That means we need to do tiling, we need to do plastering, we need to do painting, and so on. But the thing is, we can do one task only. That means a certain task depends on some another task. So, for example, if you want to paint, if you want to do the painting, you need you want that the tiling should be done first, right? So there is a dependency between the tasks. And here our aim is to find out a feasible sequence in which if we do the task, we eventually complete our whole task, right? Or eventually build a nice and office. Okay. So for that, for finding out that sequence, we use topological sorting. Okay. So I'll take one more example. So suppose in our degree, we need to complete several courses. So there is a course Maths 1, there is a course Maths 2, there is a course Stat 1, there is a course Stats 2, and there is a course of ML. Okay. But the dependency says you can complete ML only if you know all of these 4 courses. So that means the course ML is dependent on Maths 1, Maths 2, Stats 1, and Stats 2. Am I audible? I'm audible, right?
Yes, sir.
Yes,
Yes, ma'am.
Yeah. So here, the completion of the course ML is dependent on the completion of these 4 courses. But what is happening that there is a dependency between Maths 1 and Maths 2, Stats 1 and Stats 2. So it is so you can complete Maths 2 only if you can complete Maths 1. You can do Stats 2 only if you have done Stats 1. And after completion of these 4 courses, you can complete the course ML. Okay, so what can I say? I can simply say that, okay, the ML course, the completion of ML course is dependent on the completion of Maths 2 and Stats 2 course, and the completion of Maths 2 course is dependent on completion of Maths 1 course. Similarly, completion of Stats 2 course dependent on completion of Stats 1 course. So here, if you want to complete all these 5 courses, which sequence you will use? Right. So here the answer is okay. So someone says that, okay, I'll do Maths 1 and Maths 2. And after that, I'll complete Stats 1, Stats 2, and after that, I'll do ML. Right. But someone says, no, I'll do Maths 1, then Stats 1, then Maths 2, then Stats 2, and then ML. Okay. So here, whatever sequence we are writing to complete our task to complete these 5 courses, this sequence is nothing but a topological sorting. Okay. But what we will do, we will convert this real life situation into a graphical thing. So we will obtain the graph using the dependency. So what we'll do, we'll take all the courses as our vertices, and whatever dependencies is there, we'll take those dependencies as our edges. So for example, if the task B is dependent on task A, so we'll create an edge between A to B. Okay, a directed edge from A to B. So if B is dependent on A, then we will create an edge from A to B. Okay. So again, for creating a graph, we need only 2 things, vertices and edges. So we'll take vertices as our task, the given task, and we'll take edges as our dependency. So that means if the task B is dependent on task A, so that means if you want to complete the task B, you need to complete the task A first. Okay. So we'll just create an edge between a starting point from A, ending point at B, a directed edge. So using this process, we can actually convert a real life dependency situation into a graphical one. And whatever graph we will get, that graph will be a directed acyclic graph. Okay. What is a DAG? It's also known as DAG. So DAG means directed acyclic graph. As the name suggests, it's directed, and acyclic means it doesn't have any type of cycles. So for any dependency relation, we can create a DAG. We use directed because we know the direction is important. We need to complete task A, and then after that only we will complete task B. So here this direction is important. So that's why we are taking directed. Acyclic Because we know that if we have dependencies, then it is not possible to get a cycle. For example, if a task A is dependent on task B, and if a task B is dependent on task C, and if a task C is dependent on task A, then in this cycle we cannot complete any task. Because if someone says that, okay, I'll complete C first, then they need to complete A. And if they want to complete A first, they need to complete B. And if they want to complete B, they need to complete C. So it's not possible to start in such a cycle if the dependencies are like that. So whenever we have a dependency, whatever graph we will get, that graph will be automatically an acyclic graph. Okay. So that means over a real life situation, if you have some dependency task, that particular task you can convert into a graph, and that graph will be a directed acyclic graph. Okay. Now the question is to find a feasible sequence to complete our task. So that means we need to find out the sequence of vertices in which we can visit or we can complete our task. Okay, so that sequence is known to be topological sorting. So by the simple example only, you guys can easily understand that, okay, topological sorting need not to be unique. It depends person to person, it depends on their choices. Okay, so the topological sorting is not unique.
Ma'am, in
Yeah.
the explanation that task A is dependent on task B. Sorry, task B is dependent on task A, whatever it is, either way. This dependency has come into the picture only now. Earlier part of the discussions, we only talked about the graph or
Yeah.
directional graph or a non-directional graph.
Correct.
But
correct.
in the current scenario only, we are talking about a graph, a directional graph being a dependency. Is that correct?
Correct.
Earlier,
correct.
we are not discussed about that. Okay.
Yeah, right.
Thanks.
Okay. So we need to find a topological sorting. That means we need to find a feasible sequence in which we can complete our task. Okay. So as by the example only, we can observe that it is possible to get more than one type of sequence, right? So for example, maths 1, maths 2, stats 1, stats 2, ML, this is a one type of sequence, or maths 1, stats 1, maths 2, stats 2, ML, this is another type of sequence. So topological sorting is not unique. Okay. Now, for any graph, there is a particular strategy to find out topological sort of a graph. Okay, so I'll go through that strategy, and the reason why it works and why it works actually. The why is right. Why this particular strategy works is the reason is simple. So the first reason is if you have a directed acyclic graph, and if you remove one vertex from that graph. So for example, this is a this is a directed acyclic graph. In this graph, if you remove this particular vertex, okay, removing the vertex means removing the vertex and the edges associated to that vertex. Okay, so whatever leftover is there, that is also another directed acyclic graph. So for example, whatever left is here, that is also a DAG. Okay, so this is the first fact. So the fact says, if you have a DAG, directed acyclic graph, if you remove any vertex, removing a vertex means remove that vertex and all edges associated to that vertex. So if you do that, then whatever left is there, that is also your directed acyclic graph. Okay, and the second thing is, in any directed acyclic graph, in any directed acyclic graph, there is a vertex of in degree 0. So that means no matter how big, small, or whatever directed acyclic graph you have, in directed acyclic graph, you will always find a vertex. So that means it is possible to get more than once, but there will exist a vertex with in degree 0. Okay, so what is in degree and out degree? So we know that if we have a DAG, then in degree is the number of incoming edges for that vertex. Okay, number of incoming edges over that vertex, and out degree means number of outgoing edges from that vertex. Okay, so in degree, out degree. So we are talking about in degree. So in a directed acyclic graph, you will always find a vertex with in degree 0. Is that okay? These two facts. And the strategy of finding topological sorting is actually based on these two facts. So you can go in the lecture and understand how it's work actually. But But more than that, the importance is to how to find a topological sorting. Okay, the process is important than the reasoning
No.
here.
So technically, what we are saying is we cannot remove a vertex from a graph which doesn't have a zero in degree.
No, you can remove. So, for
But
example,
then
you
the
can
other
remove.
one will be hanging, no? If I remove
No,
randomly,
you will remove these edges too.
no. Let's take for example, I want to remove 3. If
Okay,
you can
okay.
erase, if you please erase that. Yeah,
Yeah.
if I say I'll remove 3, then 0 is hanging. No, okay, 0 is
No.
connected to 2 and 4. Okay, okay.
Huh. If it is not even connecting, yeah, they are connected.
Yeah.
2, 2 and 3. But what
Please
if it is not connected?
What, ma'am?
So, for example, suppose there are no edges like this. Then 0 is actually.
Then 0 is hanging. No, that's what my question. So if the 0 to 2 and 0 to 4 is missing, only 1 is there. Or 0 to 3 is there, and I remove 3, then 0 is in the air. It's nowhere connected.
Then it won't be direct. Yeah, we don't need the connectedness. We need only directed acyclic. So it's okay if it is hanging then only.
Okay.
Right. We don't need connectedness in directed acyclic graph.
Okay.
Okay. Yeah.
Ma'am, vertex of integrity 0 means?
Vertex of integrity 0 means there are no incoming edges over that vertex. For example, here, there are no incoming edges on vertex number 0. So this will be a vertex of integrity 0.
Yes.
Okay.
Okay.
So now, how to find out a topological sorting for a given directed acyclic graph? Okay, so the strategy is very simple. So it works over 3 steps. So the step number 1 is find out in degree of each and every vertex in the graph. Okay, so let's find out the in degree. What is the in degree of vertex 0?
0.
0. The in degree of 2?
1. 2.
2. Right? The in degree of 5?
2.
In degree of 1?
0.
4?
1.
4 is 1.
3?
1.
1. And for 7?
4.
4.
Right. So this is your first step. First of all, list down all in degree of each and every vertex. Okay. Now the second step is find those vertices which has in degree 0. Okay. So here in this case, we have 2 vertices of in degree 0. 0 and 1. So now what you will do, you will choose one vertex and remove that vertex from your graph and list that vertex in your topological sorting. So suppose I want to write a topological sorting here. So topological sorting means just a sequence of vertices. Okay, it's nothing new, just a sequence of vertices. So what I'll do, I'll select one of the in degree 0 vertex, write it down in our topological sorting and remove it from our DAG. Okay, and also removal of a vertex means removal of the edges too. Okay, so this step is your second step. So second step says, find out a vertex of in degree 0, list down that 0 in your topological sorting and remove that particular vertex from your directed acyclic graph. Removal of a vertex means removal of a edges too. Okay, is that okay? The second step? Yeah. Now the third step says, now update the in degree of each and every vertex. Update the in degree. Why we want to update? Because as we remove a vertex, we are also removing an edges, right? So when we remove edges, the in degree of some vertices might change, right? So the third step says update the vertex, update the in degree. So first step is in degrees. So select the in degrees. Second step is remove a vertex. And the third step is update the in degrees. Okay. So here let's update the in degrees of each and every vertex. So what will be the in degree of vertex number 2 now?
1.
1, right? Because we have removed one edge. So here the in degree will be. What will be the in degree of vertex number 3?
0.
0, correct? Because there is no incoming edges now. After removal of 0. Now what is the in degree of vertex number 1? Sorry, 4?
4 can also be 0.
0, right? Now we'll repeat this process until and unless we get, we will list all our vertices into our given topological sorting. Okay, so the next step says find a vertex with degree 0, remove it from our graph. Okay, so which vertex you want to select?
We can go with
3.
1.
Ma'am, why do we remove the vertex?
Because see, if you don't remove the vertex, you won't get a smaller graph, right? So we will use this repetitive process to kind of erase our graph.
In other words,
And also,
zero work has been done. You have finished your max 1.
yeah, so
So
something
forget
like
about
this.
max 1.
Okay,
Right.
okay.
So that
So
means we have
Task has
completed
been
this task.
completed.
Yeah.
Okay.
yeah, painting before construction has started and you put the walls are over. Now next go to painting.
Right. So that means this task is done. Yeah, that's a good point. Right. So we'll use this repetitive process again and again. So select any vertex. Which vertex you want to select? 1 or 3 or 4? You can select any one of them. It's your choice now. Well, let's go with 3. Okay. So suppose I select 3.
Normally we say no, madam, like you go in descending or ascending order 0, next you go to 1.
Yeah, that's also fine. Let's go with our convention. So let's go to the ascending order. So let's select 1. So as selected 1, written in our topological sorting, remove that 1 from your tag. After removal, update the in degrees. So now the in degree of 2 will be
0,
0, right? In degree of 4 will, in degree of 7 will
7,
change now
3.
to 3. Okay. Now
Now
there are
select
3
2.
vertices. So I'll select 2. Remove it from our tag. Update the in degrees. So
5 will
here
become 1.
1. Okay, now
Then
select
3.
3. Remove it.
5 will become 0. 7 will become 2.
5 will become 0. Now, yeah, 7 will also become 2. Now select 4.
4.
Remove the 4. And now this in degree will become 1. And now we have to select 5. Remove the 5 from the graph. Now this in degree will become 0. Now select 6. Remove it. And then the in degree of 7 will
Finally
become
do
0.
the ML.
Yeah. So now this is the one of the topological sorting. Okay. So here, since we have some choices to select which vertex we want to choose at every step, that's why the topological sorting need not to be unique. Okay. Is that okay? How to find a topological sorting?
That's
Yes,
correct,
ma'am.
madam. But why you want to specify 2-3 times saying that it is not unique, it is not unique? Because even the DFS also will not be unique, no.
Yeah, DFS also will
Even
not be unique.
BFS also will not be unique.
Yeah, whenever we got choices, it's not unique.
Yeah.
Okay. So that's all up to this particular lecture is. So they have contained some proof of the facts that why every tag has a vertex of in degree 0, why if you remove a vertex, then this will remain as a tag. So those things you go and check. But the importance is how to find a topological sort. Okay, so they have started with 1. That's also good. Okay, so this is the topological sorting we have done.
Ma'am,
1,
so
0. Yeah.
topological sorting is basically telling us how the tasks have to be done in a particular sequence.
Correct. So if you
without
follow this sequence,
without probably doing one before the other.
yeah, right.
For
Okay.
example, before whitewashing, you should have
Wall.
wall
Consider wall.
cementing has to be done.
Yeah.
But once you finish bricklaying and put the whitewash, when will you do cementing?
Oh, on top of painting.
Right.
Okay.
Okay. So is there
Yes.
any doubt in these topics?
Ma'am, I have to ask one question from assignment.
Yeah. So now, yeah, we'll go to assignments only now.
Ma'am, practice assignment question number 1.
Yeah, just 1 second. I'll share my screen.
Today, unusually, the strength is almost 1.5 times. 7 to 8 people come today, 30 people are there.
No, it happens.
But I think in any case, compared to the number of people who are writing the exam, this is significantly less. I don't know why they are not
Very
utilizing this.
less.
Prakash sir, positive
Uh,
thinking. I'm telling it is increased.
increase, yeah, understand, but still,
From
if you,
100%, it has become 150 now, one and a
yeah,
half times more.
percentage
As
wise, you're
the,
right. But
as the
if
end
you,
term is approaching, people are becoming interested and they wanted to
mm,
do. That's why it has almost 50% increase in the attendance.
yeah,
Madam,
Uh,
if I may ask, when out of the present topic, this
hmm.
bonus marks, when it will be displayed, ma'am, and what is the criteria you are going to use?
Bonus marks for which? For what?
Max one, there is one
Um,
concept called bonus marks. So you are
oh,
not aware.
no, I'm not aware of that.
2 marks is being given. You do certain works like
Okay.
mock test and all you are doing, no, madam. You
Mm-hmm.
based on that 2% of marks, 2 marks will
Mm-hmm.
be are added to the end term score. I mean, rather the total score
They
grading.
will add into total score. So they
Yeah.
will compute the total score using your quiz 1, quiz 2, GA and all those things. In that thing, I think they will add.
Okay. You are not aware of that, is it, ma'am?
No, no, no. I am not aware of that.
Okay. Okay. Thank you, ma'am. Proceed, ma'am.
Okay. So this is the question. Suppose we obtain the following DFST rooted at node 0 from an undirected graph with vertices 0 to 10. So which of the following cannot be an edge in the original graph? Okay. First of all, it's a DFS tree. It's not a BFS tree. So here we can use the randomness. So let's think a little bit. So suppose 1, 4. Which of the following cannot be an edge in the original graph? Okay. So what you will do for such type of question, what you will do? You will create a graph. So this process usually always work. Okay. So create a graph with that edge. So that means what you will do, they use the same tree, but insert an edge from 1 to 4. Okay. So now suppose uh, this is your original graph, and now apply DFS process here to find out the tree. And if you get back your original, if you get back to the question tree, whatever tree is going given in the question, then the answer is yes. It is possible to have a graph with this particular edge. Okay. So now let's figure it out. Is it is possible to get this particular tree back or not? So I think the answer is yes here, right? So you'll start with 0. You can go to 1. So from 1, we can go to, so now from 1, you have choices. You can go to 4, you can go to 3. It's up to you. But since we want to get back to our graph, which is given in the question, I'll select 3. Okay. Then I'll go to 4. And now from 4, I don't have anything new to visit. I'll go back to 3, then go back to 5, right? Then go to 5. That from 5 also, I don't have anything to visit. I'll go back. And I think you will get your tree, which is given in your question. Okay. So you understand the method, what I'm doing here?
We
I'm
can look
saying,
for cross edges, right? So because cross edges would cause a problem in the DFS because they won't
uh,
contribute to being an
yeah,
aging.
correct. Yeah. So suppose there is an edge between 3 to 7. Now you cannot backtrack to 1. You have to visit the new vertex 7. Right? So for example, okay, so let's observe these options only. So that means it is possible to have an edge from 1 to 4. So that means this option is wrong. From 0 to 4 also you can have the edge by the same reason. You can also go back to this method, create a graph with that edge, find out the DFS tree. So this is also not true. But 7 to 10. Okay, so now observe this edge 7 to 10, which is among the branches, right? So this is an edge from 7 to 10. Okay, now suppose that this is your original graph. And now apply a DFS method to this particular graph and obtain a tree. So what happened? I'll start from 0. From 0, I'll go to 1. From 1, I'll go to 3. From 3, I'll go to 4. From 4, I'll backtrack, go to 5, go to 3, go to 1, 0, and so on. I'll go to 2. Then from 2, I'll go to 7. Right? But I want my tree back as the whatever given in the question. I'll say that, okay, I'll choose 8. From 8, I'll backtrack to 7. From 7, I'll choose 9. But now from 7, I cannot go back because I have a choice here. I can go
I
to 10.
understood, ma'am.
Right?
Ma'am, I understood.
Yeah. Okay.
But you can go from 2 to, instead of 7, you can go to 6 and then go to 10.
But see,
After that-
we want to get close to the graph which is given in our question. Okay. So now here at this step, I cannot get a graph which is given in the question. I have to connect 7 and 10.
Okay.
Right. So this will create a problem. Right. So this method actually usually works. So as you guys told that cross edges, right? So cross edges will create a problem.
Ma'am, but how can it go to 7, 10, and 6? Because it will stop at 10, right?
No, from 10 also I have a new
Yeah.
vertex which is on
Oh, you
Vertex.
can go to 6. Okay, okay. It's
Right.
it's a non-directional.
Yeah, right. Undirected, right? Okay. So let's go to the second question. Any doubt? I'll take the doubt because there are so many questions. If I took each and every question, then we have to sit up to 2. Any doubt from practice assignment? Any other question? Any other doubt from this assignment? Let me check.
They're not come to that point, ma'am, yet. Still to be done.
Okay, okay. It's okay. We can discuss this in the week 11 lecture too. So
Yeah.
I don't think there is any other session for this course. Except this one. Okay.
Can you please conduct special session for calculus? Hello?
Special session for calculus. So we have revision sessions, but
Okay.
other than that, I don't think. Revision sessions and TA sessions. If you want, we can have a TA sessions.
Okay.
Okay, so this question is not that tough, but little bit theoretical. So that means first you need to understand what are the things is going on here. Okay, and then go for solving. So here this A1 and this A1 is different. Okay, so here this particular A1 is the A1th entry. So that means A1 is equals to A1. This A2 means the second entry of column A. So this A2 is B1 minus 10. Okay, so this B1 is A1 square. So whatever A1, B1 is used here, they are different from these A2, B2s, whatever used in the columns. Okay, so these are the entries. So that means this is the first entry of A1 column, fourth entry of A1 column, second entry of A1 column, and so on. Okay. So this is the only confusion this question may cause. Other thing. So once you figure out that, then it's easy. Any other question?
What you said, I don't understand about the first question.
Yeah, so I was telling that here they are written this A1, B1, A4, B4 in the options, right? So
Okay.
these are the entries. So that means A1 is the first entry of
Okay.
column A.
Okay.
And here this A1 is the first entry of column A. So that means here A1, the value of A1 entry is A1 itself. The value of B1, so that is the first entry of B1 is A1 square. Okay. Right. The value of A2 will be B1 minus 10. The value of A3 will be B2. Right.
Okay.
So these are the entries. So that means the first entry, second entry, whatever options is given. And these are the actual relations between entries.
Now, what does the graph indicates?
So graph indicates the dependency. So that means here what is happening? The B1 entry is A1 square. So that means this B1 entry is dependent on the entry A1. Okay. So you have to figure out what are the dependencies there.
Oh, as per the arrow.
Yeah, as per the arrows.
Okay.
And judge which will correctly represent this particular column, this particular spreadsheet. Right?
Okay.
A1 will have 0 in degree.
Yeah, A1 will have 0 in degree.
Ma'am, 10.7.
Okay. Which question? Only one question is there. No?
One is it.
So consider the following directed graph. Suppose DFS of this graph is performed from node A. such that when we visit a vertex, we explore its unvisited neighbors in alphabetic order. Okay, which of the following options are correct? So what you will do, we need to find out forward backward edges, right? So first of all, consider a DFS tree of this particular graph. Okay, so I'll start with what node A because it's already written, and then visit vertices in an alphabetical order. So there are two vertices of A, B, and C. So from A, I'll go to B, right? Now from B, I can go to C, I can go to D, right? So I'll go to C, right? From C, I have only one choice, which is F. So I should go to vertex number F. And from F, I have an edge which is connecting to vertex number D. Okay. So now this will be your DFS tree. So now we can figure it out what are the edges. So here we have a tree like this, A, B, then C, D, and C, F, and D. Okay, so this is CF edge. So CF edge is there, but CF edge is not a non-tree edge. Okay, so these forward edge, backward edge are non-tree edges. So this is not a non-tree edge, right? It is an edge which is used in our tree. So that means that's why it's
Got
not
it,
a
ma'am.
forward edge.
I was considering CF as well.
Okay.
Got it.
Any other doubt?
Here FD is a backward edge. That is also not true because
No,
FD is
FD is used in our tree.
okay.
So that's why it's not a backward edge.
And AC is also a forward edge. That is also not a one.
AC is forward edge, that's correct, because it haven't used and it is in the direction of tree.
Then
So,
CFS is also a forward edge only, no?
no, but this is used in tree, right? So these are non-tree edges.
AC is also used in tree.
Yeah,
Oh no, not from B. Only
AC
from
is,
B. Okay.
yeah, AC
Not
is
direct.
not.
Okay.
Any other doubt?
Of course, recordings alone. Hello.
Hello. Yeah.
So recordings alone, you have to find that. Sometimes it is not getting featured in YouTube live.
Recordings, na lectures recording.
Yes.
You
Usually
can go to the calendars.
No, it is not. The access is not given.
Access is not given. Yeah, I'll talk to them. Yeah, someone already pointed out that access for week 9 lectures, na?
Yes, week 9 lectures.
I think this lecture live is streaming.
Yeah, live is streaming the previous ones, not this one, the previous ones.
Yeah, I'll inform them to give access to you.
And why there is no email ID given to any candidate?
Why there is no
official email ID given to anybody?
Official email?
Yeah.
So I think they will give after a term, maybe. After completing a term, they will give you the access of discourse and all those things. If I'm not wrong.
Ma'am, for that quiz 2 answer sheet, you will be informing them to upload?
Yeah, I'll inform them to upload because I cannot upload it.
No, the individual answer, not the answer sheet, ma'am. The individual scoring sheet. When I log in, I think some other lady also was mentioning about that she has expressed this earlier before I asked.
Yeah. So you guys need to fill out a G form regarding your scores, right? You're okay with your scores or not, something like this. But
yeah,
you
something
don't.
like that. Yeah, we don't have the sheet access to that sheet. It's not only the quiz 1 is uploaded. Quiz 2 is not yet up.
Okay.
I don't know about others. Narayan sir, you're able to see your sheet? Pardon?
I'm not first student. I'm old student. I'm able to see.
Oh, okay.
Okay, so it's the case for I think some people.
Initially, G form was also not available. But when I mailed them, now it is available. Now we can fill the G form. But the thing is, we need that quiz 2 question paper.
Question paper means your answer key, right? Your response sheet.
No, ma'am. For the whole set of question paper, there's a answer key has been given. But what we want is the we have answered. We have given our answers to the in the exam, right?
Mm-hmm.
Whether those answers what we have given are right or wrong, we need to
Yeah, you
give a
want
feedback.
response sheet, right?
Ha,
Whatever you
that
have done in exam,
exactly.
that
Yeah, that
particular
is
thing.
missing. Yeah,
Mm-hmm.
that is only available for the quiz one. Quiz two is
Mm-hmm.
missing, but we
Yeah.
have to respond back by tomorrow. How can we respond when we don't have access to the sheet?
Mm-hmm. Yeah, I'll inform them about these two things.
Yeah. I don't know. It's for everyone. It's like that, or it's only for a few individuals. Because at least I don't see. I think the other lady also mentioned the same problem.
Sir, why
Yes,
I
sir.
did not see, no?
Huh.
I am getting 64 as per the whatever the answer
Dashboard.
sheet is showing. Dashboard is 72.
Okay.
That's
So
why
I am getting dashboard is more than what is written.
that's why they
Yeah,
don't
the
have
same
problem.
thing is happening with me as well. My dashboard marks and score checker marks are not matching.
Okay.
There is a
Yeah.
mismatch.
Mm-hmm.
So what we should do for that? Be silent or
I
they'll
don't know.
change?
I have mailed them.
Yeah, I'll also talk to them.
No, in that case, they will reduce my marks.
I don't know.
Let me see.
Okay.
Naren is this, na?
Yeah, ma'am. Which email address you are
Ma'am, my
emailing?
case as well.
Which what? Email address?
No. Yeah, I think I don't know. Someone was telling that they have emailed for a response. Which email address so that I can also send that email to
Sir,
register my.
I'll tell you. It is DS support something. I'll just
Okay.
tell you.
Yeah, if you can put it in the chat, I can copy.
Yeah.
Yeah, give them 2 to 3 mails. They won't work until and unless there are so many mails of the same issue.
Yeah.
Okay, so this is type this V alpha. This is bracket B1, B5, B8.
Yeah, I figured out that. Okay, thanks,
Sir,
ma'am.
I've
I got.
shared the mail ID.
Yeah, I got it.
Ma'am, please show that question.
Which question? This one?
Yes, ma'am. Yes.
Yes.
Ma'am, option number B means ma'am, double slash at the last of the option.
Yeah, this is just a typo.
What
You
it
can
means?
consider it as B1, B5, B8.
No, ma'am. What it means what it explains.
So this question says in a factory there are 10 buildings.
Ma'am, not question, only answer.
Yeah, so this V alpha, this is nothing but simple set. This B1, B5, B8. It's just a typo. So in coding they use this slash to create a bracket, but it may haven't worked here. So this is just a set. So as the first option B1, B5, B7 is there. This is B1, B5, B8, B1, B7, B9, and these are the same B's. Whatever B is 8, these are written here, no? The same things are there in the option.
Ma'am, both are same, which you
Yeah,
have
both
written
are.
and
Huh,
which you have written and
this thing.
both
Yeah,
are
both
same.
are same.
Okay, ma'am. Thank you.
Just a typo, right? Okay, so let me see. You have any other doubt? Any other question? Any topic which is not clear yet? Any topic you guys want to recall? Okay, if not, then we can wind up our session here. But if you guys have doubts, then I can take them. Because see, I cannot solve each and every question. That won't be fair, right? So, hello.
Yeah, ma'am. Okay.
Okay. So yeah, if no doubts, then we can wind up our session here. Thank you guys for joining.
Thank you.
But if you have doubts, you can ask. I'll stay here for 5 minutes and then
Thanks for the session.
thank you
But
guys.
if we are, topic of testing from last time when we joined the conference, the SSC was that important.
Prashant, your voice is echoing actually, so I'm not able to understand.
Am I audible now? Is
Yeah,
it clear?
yeah.
So what I'm asking is there any, particular exam questionnaire that can come? Like you have mentioned, SSC is most important, right?
Hmm.
Like there
Yeah,
any?
so see, 3 topics: vertex cover, independent set, coloring.
One
These
second.
3 are important. So there will obviously one questions from among these 3. One or more, it's possible to get one or more. Vertex cover, independent set, coloring. Now next is DFS, BFS trees and topological sorting, obviously. Right? DFS, BFS process and topological sorting. So you can take care of this 6, at least there will be question from this 6 topics.
Okay, let's cover independent, DFS and DFS.
Coloring
Topological
also. Vertex coloring.
vertex
Graph
color.
coloring.
Okay.
And also we'll discuss some of these in revision sessions too.
Now, sometimes I don't attend. The thing is that I have to be in office during that time. We have usually, miss all the sessions. That is the problem. I cannot sit in the office and continue my lessons.
Which? What?
No, sometimes I don't have the opportunity to attend the sessions. That is the issue. The working employee, it is very difficult. I cannot sit in my office and they don't know that I'm learning. Yeah.
Right. So yeah, you can obviously these 6 topics are important. So if you won't able to do anything else, at least do these 6 things.
Okay, thank you.
Okay, so thank you guys for joining. See you in the next session.
Thank you, ma'am.
Thank you.